Hello great people, feel welcome for today's lesson. This is Mr. Makokha Fredrick Matseshe. Lesson 1 under structures, that is beam design. We have methods of design structures. In structures, 1, we have elastic method, also known as modular ratio method. We have 2, plastic method, also known as load factor method. We have 3, limit state design method. And this is for elastic method. This is for HND, still here for HND, Higher National Diploma, and this one, it's normally used under diploma. So we are dealing with these two. For higher national diploma, we only deal with elastic method, stroke modular ratio method, plastic method, or load factor method. So let's start by elastic method, stroke modular ratio method under beam design. We have procedure of beam design. 1, this is a HND, and it is elastic stroke modular ratio method. 1, determine the minimum depth. This is abbreviated as D min, and D min is given by the formula, the beam span. So, and this is the depth into bracket all over ratio, and the ratio will get from the table 13 of CP114, which I'm going to share with you. Then number 2, we have establish the loadings. Establish the loading conditions of the beam. Establish the loading conditions of the beam. Number 3, calculate the bending moment, i.e. if it is a UDL, uniformly distributed load, for example, can be this way. This is length, this is intensity of UDL. To get the bending moment is from the formula WL squared all over 8. That is the formula. Number 4, determine the effective depth, abbreviated as D1, using the formula D1 is equals to, under the same square root M max all over K multiplied by B, where K is given by the formula 1 over 2 PCB A1 N1. Then we'll determine the overall depth D from the formula d1 plus insert, of which insert is the diameter over 2, half of the diameter, plus cc. Cc is concrete cover, and we normally assume cc to be 25 millimeters and bar diameter to be 20 millimeter. So then you are required to compare. You will compare D and D minimum and adopt the greater. Adopt the greater, which means you will take the greater. Then you will get the actual D, and the D actual is from the formula D minus insert, and you know the insert here is this one. Then 5, you have determination of area of reinforcement, that is still ST, using from the formula now AST is equals to Mmax all over PST multiplied by LA, the lever arm, and you will select the suitable diameter from the respective tables. Now number 6, you will check for shear. Normally say the calculated shear FQ should not be greater than the permissible shear. That is from the table 6 of CP114, which I'm going to show you. But here for calculated shear is from the formula Qmax all over lever arm LA multiplied by the B, the breadth of that beam. Q is the shear force maximum, and Q small is the shear stress. Good. Now we continue. We have we go for 7. The procedure number 7, we have bond stress. Bond stress, we normally say F, the calculated bond stress local, should not be again greater than the permissible bond local. This is still from the table 6 of CP114, Code of Practice 114. But for calculated bond is equals to Qmax all over lever arm LA multiplied by O. But this O, it is the total perimeter of tension bars. Okay, we'll calculate. This is local. This is under local bond stress, and you have 2, the average bond stress. Average bond stress. Here we say grip length grip length should not be greater than bar diameter multiplied by permissible stress in steel PST all over 4 PB multiplied by the average bond. This is still from the table 6 of CP P114. Then lastly, the last procedure is detailing of the beam. Good. We have the detailing of the beam. Now, for instance, this question, let us use a question here now. We have a question here. An example of a question under beam. Example 1 now. A simply supported beam of rectangular section of a span 6 meter is to carry a lively UDL of 6.2 kilonewton per meter. The breadth of the beam is restricted to a width of 225 millimeter. Design and detail the beam given the following data. We have data. Given the data, self weight of the concrete, it is 24 kilonewton per meter cubic. That is the density of concrete. Modular ratio M 15. Concrete mix 1 to 2 to 4. Area of reinforcement, we have 140 Newton per millimeter square. So it means this is a permissible under steel, permissible area under steel. CC concrete cover 25 millimeters, and it is 20 marks. Now before we tackle this question, let me show you parts of the sum table. And this is CP 114, code of practice table 114, and we can check into our table. This is table 6. Table 6 said or called permissible stresses for nominal concrete mix with Portland cement for Portland blast furnace cement and with aggregate complying with BS. So this is CP114 and this is table 6. This is mixed proportion. We have here the first one is 1 to 1 to 2. The second one is 1 to 1.5 to 3. And we have 1 to 2 to 4. We have compressive, and this is bond. This is shear. This is the table 6 called now permissible concrete stresses. And you have again table 13 of steel CP114 code of practice. Table 13 called permissible values for span over depth ratio of beam and slab. Now here we are dealing with the beam, and the question was saying it was assembly supported, which means we'll go for 20. If it was continuous beam, if it was continuous cantilever beam, we'll go for 25 and 10. But here the question has said that a beam is simply supported, so we pick 2 as your ratio in determination of minimum depth. Again, we have this table here, area in millimeter per number of bar here, and we have area in millimeter per meter width. This is for spacing, and this is for a number of bar. Now, under solution of it, we have under solution, we start from sketching that beam. We sketch the beam. So under solution, we sketch that beam. They said it's a beam of span 6 meter and it carry a UDL of 6.2 kilonewton per meter. Let us sketch this section of the beam, a section. This is a section given the breadth to be 225 millimeter from the equation, and we want to find the D minimum, this D. We want to find this one. So it means we'll use from the first procedure, we say we determine the D minimum. So D minimum is from the formula span over ratio, and we have span as 6 meters, so into millimeters it will be 6,000 millimeter all over ratio, and ratio we said it was assembly supported, which means we take 20 from CP 1140/13. So here when you divide it out, it will be 300 millimeters. So this 300 is here, 300 millimeters. That is going to be your D minimum. This is task 1. Task 2, loadings. We establish loadings. Condition for the beam. Under loadings, we have self weight of the beam, which is 0.25 multiplied by 0.3 by 24. When you multiply out, it will be 1.62 kilonewton per meter. Then we have live load or imposed. It is also known as imposed load. The imposed load, they said the live UDL of 6.2 kilonewton per meter. So when you add this one to get the total loading, when you take this one plus this one, it is 7.82 kilonewton per meter. Good. Now task 3, you calculate bending moment. So bending moment, BM max, we have the loading now, it is 7.82 kilonewton meter. What about the length? The entire span is 6 meter. So we have the formula. The ultimate design moment is equals to WL squared over 8, which is 7.82 by 6 squared L squared all over 8. So this is 35 point, when you multiply out, is 35.9 kilonewton meter, and the SI unit of bend moment is kilonewton meter. That is the SI unit. Is very important. You have task 4. Task number 4, we have effective. We find effective depth D1, abbreviated as D1. D1 is from the formula the square root of M max all over KB, but remember K was 1 over 2 PCB N1 A1, but PCB here is from the table, PCB from the table 6 of CP114. You have here the mix. We are using the mix from the equation, it was 1 to 2 to 4. Now our PCB, it's compressive due to bending, which is 7. Now we pick 7. So it is 7 from the table of CP114. Table 6, that is table 6. But N1 is equals from the formula, is given by the formula 1 all over 1 plus PST all over M PCB. But A1 is equals to 1 minus n over 3. So you must find n for you to get a1. You must find n1, sorry. So we continue. N1 is equals to 1 all over. We have 1 plus PCB plus PST, which is 140 from the formula. PST was 140 from the equation, all over 15 M, which was M, M15 PCB 7. So we have multiply by 7. Here when you simplify it, you will get your answer as 0.429. And what about A1 is 1 minus n, which is 0 now, 0.429 all over 3, and the answer is 0.857. Now let us find general K, since we have N1 and A1. So is equals to 1 over 2 half PCB 7 multiplied by 0.429 multiplied by 0.857. So the answer is 1.287. Insert the parameter we were looking for within this equation. Now the formula to get D1, the effective depth. Since we have KB and M max, now we just insert directly within the formula. So we have square root of 35.19. We multiply now by, it was kilonewton per meter. Now we multiply by 10 raised to 6 to change into Newton per millimeter. So to change into Newton millimeter. So we have 35.19 multiplied by 10 raised to 6 all over 1.287 multiply by the breadth. It was KB. Now the breadth was 225. So you have here your answer as 348.60. So let us find the overall. The overall now. D overall is equals to D plus D1 plus insert. And insert we have, which is 348.60 plus 20 bar diameter over 2 plus 25 cc, that is concrete cover, is going to be 383.60 millimeter. So just say 400 millimeter. Compare D minimum and D minimum is 300, which is less than D actual 400. So let's adopt 400 millimeter as the depth. We adopt the greater. Okay, now we have actual D. Let us determine actual D. Actual D is equals to D minus D overall minus insert. Overall we have this one, D 400 minus insert. Insert is 35. When you take this one, 20 divided by 2, that is 10. 10 plus this one is 35. Now we subtract 35 here. We have 365 millimeter as your D actual. This is D actual. Let us now move to task number 5. Task number 5. Task 5. We have task number 5. Task number 5. We have AST, area of steel reinforcement, area of steel or area of reinforcement. AST is equals to M-max all over PST multiplied by LA, but LA is equals to A1D actual. LA now is equal to 0.857, which was this one, A1, multiplied by 365 D actual, this one. So the answer LA is equals to 312.81. Now area of steel, particularly ST, is equals to 3519 multiplied by M-max, and that was M-max by 10 raised to 6 all over 1 PST 140 multiplied by 312.81, which is 803.55 millimeters squared. So from the table of from this table now, from this table now of area in millimeter per number of bar, we can find this 803. This is the same as 804, approximately 804 millimeter square. And you can see 804 here. 804, this is the 16. The number of bar are 4. Now we say there is something to note. NB, we say if PST, which is 140, if we normally say if PST is 140, this is indication that it is round bar. But if it is at least 175, it is at least 175, then it will be Y bar. For our case, it was 140. Now we say provide for R16, which was 804 millimeter squared as the area. Task 6, check for shear. The calculated shear should not exceed PST.